All right. Yeah, so I tried to give kind of a taste of what we will be talking about and this part. Now let's get back to a bit more structural kind of view of that. Lagrangian traffic control, I'll talk about what it is first, and then basically give, I'll try to present how you could think of a traffic control loop by using only the information that comes from these kind of connected vehicles, and only using these connected vehicles to actually do some work in the system, so to do some actuation. So first I will talk about how can we think about actuation and sensing in a Lagrangian framework. I will talk about three problems or three parts. The first part will be traffic state reconstruction and prediction. Then we'll do a bit about model learning, talk about the control law, and then I'll show in the end some simulations, some simulation results. All right. So this part I already gave as a bit of a teaser, just to really quickly recount. From the connected side, what the vehicles can provide us is highly detailed traffic data, trajectories, or either of them themselves or also of other vehicles potentially, as well as enabling cooperative control schemes, which we will not talk about here. What we will talk about when it comes to control schemes is this second part, how we can use autonomous vehicles for Lagrangian actuation. All right. What do I mean by Lagrangian traffic control? So this term comes from the physics, where you have an Eulerian approach to modeling, for example, fluid dynamics, and a Lagrangian way of modeling them. When it comes to the Eulerian method, if you're thinking about it, basically has to deal with some sort of fixed volumes and thinking about what happens in this stationary volume. So if you're thinking about a flow of a liquid, it's kind of like sitting on the bank of a river and then measuring the flow pass by you. That is one way of thinking about things. And in the perspective of the traffic control, these classical traffic control methods are exactly like that. So you have stationary sensors that are sitting at the bank of a river and measuring the water flow, and then you have stationary actuators that do some sort of control, again, wherever you can find them. As a contrast to that, you have the Lagrangian way of thinking about things, which is more like sitting in a boat and floating down the river, so that your boat floating essentially describes what's happening with the flow of the river. And it has more to do with particles inside of the system. It's not linked to a certain volume that is stationary. And thinking about traffic control, what we would have in this paradigm is moving sensors and moving actuators. So actuators that are inside of the flow itself, a part of the flow. So the full control loop that I have in mind looks something like this. So first, let's identify kind of the things that we remember from the control loop from before. For one, what is the process? Well, we're controlling the road. So we're controlling some sort of a road system. In a sense, that is the process that we want to influence. What are the sensors? I said that we will be using localized measurements and trajectories of these connected vehicles. So you can see in green the flow of this basically sensor data. What are the actuators? Well, again, it's these connected autonomous vehicles, by the way, shown in gray here. And in blue, we have the control actions that are kind of communicated to these connected vehicles. Now, what do we do with the measurements? Well, one thing is we want to feed those measurements to the control law in a bit of a roundabout way. I'll come to that. But another thing that we want to do is we want to use these measurements to try to learn what the traffic model itself is. Well, how do we think about the traffic model? How do we, which then will inform us, once we get this traffic model, it will inform us how do we do the prediction and reconstruction of the traffic state. And that is important to us because we have a control law. So we will have a prediction based on the measurements, based on the control actions in the future, and the prediction that we, and of course, based on the traffic model, and the predictions that we get from this model, we will feed to the control law, and then come up with some control actions based on these predictions. So basically, we can tell the prediction model, okay, I want to do this. The prediction model spits out, okay, this is what's going to happen, and then we adjust that until we're satisfied with what's going on. So this is basically the outline of the second part. I'll go basically into the different parts of this control loop one by one. First, I do need to revisit the traffic model. And now we're back to the Lytle-Witham-Richards. So we have the fun with the space discretized model. Unfortunately, once you start talking about Lagrangian control, there things get a bit more complicated, because with stationary sensors and stationary actuators, you can kind of build these cells in accordance to that. In this case, you will have these vehicles just moving around the road. So it becomes very hard to track them in an appropriate way if you want to have a kind of stationary discretization in space. So stationary grids, like these cells that do not move, whose boundaries do not move. So in that sense, we do need to think about the model in a bit of a different way, and the PDE type model that does allow us to do that. So there will be a bit, this is a bit of, okay, I'm talking about LWR, it's a well-known model. The flavor of the model that I'm talking about here is a bit peculiar. And that is because I'm going to be talking about LWR with piecewise linear flux functions and piecewise linear initial conditions. So piecewise linear initial conditions, it's basically the same thing that you have when you have discretized traffic state discretized in space. Piecewise linear flux functions, I mean, you could have just a triangular flux function that is definitely, that is one piecewise linear flux function that works. I will allow this flux function to be of a more generic shape. And you might even say that, okay, this is, you can't have a flux function like this. The mathematical side says there's no problem with this. The traffic side says, yeah, maybe you're right. Maybe we shouldn't have a flux function that looks like this, but the math eats it up and it's not a problem. There will be a lot of plots that look like this in this part. So what I'm showing here in this case is the traffic density, and the traffic density is color coded. On x-axis we have space, on y-axis we have time. You might be more used to a flipped picture where space is on y-axis and time is on x-axis, but yeah, I'm sorry, this is how we're going to roll. This is a more kind of a more common approach, at least with the more applied math types, as opposed to the more traffic people. But yeah, so what we have here is we have some congestion. Yeah, by the way, warmer colors indicate a higher traffic density. So what we have here is we have some congestion at time 0. There's some zone of congestion. Then this congestion over time will dissipate, and you can see a higher traffic density discharging from it. All right, nothing too fancy right now. Another specificity about this model is that I will allow the flux function to be defined piecewise in space. With some, okay, first, why would I want to do that? Well, let's say there's an accident at this point of the road, and this lane is closed for over some zone. So you might, I mean, obviously the traffic flow around this zone of the accident will probably, well, I mean, obviously it will follow some different type of behavior compared to traffic flow just anywhere else. So that what we can do here is we can say, okay, this particular zone is actually described by a different flux function, which in general will be a scaled down version, or you can have a different type of a flux function, whatever you want. But the idea is the capacity, because one lane is closed here, the capacity is going to be lower. That's more or less the only thing that we're modeling. Now, I said that we need this zone to have boundaries that move in a certain way. We can actually have these boundaries move as long as they're moving at a constant speed. As long as they're moving at a constant speed, the math eats it up. It's no problem. Why might we want to do that? Well, I will come to that when I talk about Lagrangian actuation, but this is something that you might see. So you might have some moving bottleneck, spoiler alert, that is doing something to the traffic. All right. I'll try to go really quickly over this, but because I'm talking about the stop and go waves or phantom waves, I think it is worthwhile to talk a bit about kinematic wave theory I'll try to go extremely quickly through this. Basically, what I'm trying to hint at here is how do we deal with solutions of this kind of a model? How do we deal with this PDE? For one, looking at this PDE, if the initial traffic is homogeneous, so constant everywhere, equal to some rho 0, well, nothing happens basically, because the gradient or the gradient of traffic flow is 0, which means that nothing will happen to the traffic density into all the time into the future. To deal with these kind of PDEs and describing the solutions, one thing that you will typically have to study, at least in this very specific case, are the so-called Riemann problems. And the Riemann problem basically deals with what happens at the discontinuity between two different traffic states. For example, if we have some free flow upstream and then some congestion downstream, what will happen at this point? Well, it depends on the state upstream and downstream, but let's say the upstream you have this x to the left, and downstream you have this traffic state to the right. What in this case you have is you will have a shock, and then based on the flow upstream and downstream, this shock will either propagate upstream, as we have here, or downstream. And actually the slope of this line connecting these 2 points will inform what is the speed, the propagation speed of this wavefront that you have here. So that's fine if you have free flow coming into congestion. What happens if you have the reverse situation when you have congestion upstream and free flow downstream? Well, here you have a bit of a different case. For mathematical reasons, what you end up doing is not going directly through this flux function or fundamental diagram, but you need to go up. So you need to go along the upper concave envelope of this flux function, and that's called the rarefaction. So what you get is a rarefaction wave. You can think about it as it has to do, maybe you can understand it through this notion of limited acceleration. So maybe you cannot accelerate from this speed to this speed directly, but you have some sort of a gradient, and there will be, in essence, a zone in the middle where you're moving at capacity. So where you're moving at free flow speed, but you're at capacity when it comes to the density. Not going to go any more into details, except to say that this basically is the situation that we want to model at the downstream end of a phantom jam. So this is when I was talking about capacity drop, when I was talking about especially capacity drop in the framework of phantom jams, this is basically it. So what we need to know is what is the traffic density discharge, or rather, what is the traffic flow discharging from this capacity, from this congestion. If we know what the traffic density, traffic flow and traffic density discharging from the congestion is, then we know what the outflow is. If we know what the outflow is, then we know what we need to set the inflow to in order to dissipate the congestion. One way to do that is to say, okay, what we want to do is we want to limit the wave speed of the rarefaction. I'm not going to go into any details, but the effect of this is, instead of going up this, all the way up this flux function, you instead kind of cut through it. And because of that, you are now not dissipating this congestion at capacity. Instead, you're dissipating it at this reduced traffic flow. And this reduced traffic flow, note that if you increase the congestion density up to the maximum, this outflow will also decrease, because you just take the line from here, draw it up, intersects the free flow branch around here, you get the lower outflow. How much sense does this make when it comes to traffic data? I'm not sure. But what I am sure is that this is one way to model the capacity drop that you get from a phantom jam. Might be a simplest one, I don't know. For me, it sounds like a reasonable way to approximate. Okay. Finally, let's talk about what we can do for the traffic if we are controlling individual vehicles. Well, we can do a lot, actually. You can do something like this. Well, if you're a police car, you can do something like this. You know what this is? It's called a traffic brake. I'm not sure if people do that in Europe, but in the US, if for some security reasons you need to clear the highway, you can get a police car, and then the police car just goes left and right and essentially causes all of the vehicles to slow down behind it. So yeah, you have one vehicle and it is controlling all of this traffic flow. So that's quite powerful. Maybe we do not want to be as severe though, and maybe we don't have a police car. So what can we do instead? Well, if you're thinking about how we can control, first, let's not think even about how we can control the traffic. How can we control an individual vehicle? And really, there are only two things. We have its longitudinal motion, which we can control by setting its reference speed. And we have its lateral motion, which we can kind of control by maybe issuing some lane changing commands. So go to the left, go to the right, keep to the right, and so on. That's basically all there is. Well, all there is that is relevant to the road, unless you're doing some really, really dodgy business. And that is all we have when it comes to a single vehicle. Now we come back to the platoons, because once you have a platoon of vehicles, then you get a bit more, you can get a bit more kind of structured way to control them. Now, the longitudinal motion stays basically the same, because all of the follower trucks will be moving at the same speed as the leader. That's okay. But with the lane changing commands, you can start getting a bit more fancy, and you can do things like maybe we can tell this truck or this truck to change lanes. And now all of a sudden you have a formation of trucks that is blocking two lanes. So you can imagine that if you have a formation like this blocking two lanes, that will cause more of an effect on the rest of the road. And I mean, you get this kind of spontaneously when two trucks overtake each other. You have elephant racing, I believe they call it. So overall, what we end up doing with these vehicles is, so for one, thinking about the microscopic effects, there we can talk about string stabilization, controlling the reference speed in order to kind of stabilize the flow. All of those things exist on a microscopic level when we're thinking about individual vehicles. On the macroscopic level, there we want to control, essentially what we want to do here is control the local traffic flow. That's all we can do with these vehicles. So these vehicles are at some place, they can have some sort of a local effect by doing whatever they're doing. That's what we want to control. The way we're doing that in this case is by considering to be moving bottlenecks. So I think I mentioned it before, a moving bottleneck, simply a slow moving vehicle that restricts the traffic flow. All right. How do we model that? Where I did mention that we can have a zone where a different flux function describes the evolution of the traffic, and that zone can move. Well, this is why we want it to move. Because if we have that zone move, then it is obviously a moving bottleneck. What we can do is we can have some sort of a scaled down flux function that corresponds to how many lanes we are blocking, essentially. So, or rather, in this case, it corresponds to how many lanes there are left. So if we're blocking 2 lanes out of 3, then you might expect this flux function of the rest of the road to be scaled down quite a bit. And then if you're blocking only 1 lane out of 3, then it is scaled down less. So it's the simplest thing you can do is say, okay, it's just proportional to how many, what area on the road that we're occupying, or what width of the road we're occupying. Now, once you pose the LWR with these space-time dependent flux functions, what you get is you essentially have the boundaries where the boundaries between the flux function that describes the rest of the road, which is the black one, and the flux function that describes the road next to a moving bottleneck. And what you can do is solve the Riemann problems at these boundaries. Or what you need to do is solve the Riemann problems at these boundaries. I'm not going to go into too much details. Essentially, what you get is that depending on the speed of the moving bottleneck, you will have different, for one, if the traffic flow is light enough, then maybe you will not really affect it at all. So if you have 1 lane of vehicles on a 3-lane road and you block 1 lane, I mean, it doesn't really matter. There's not enough flow for this moving bottleneck to really impede it. But once there is enough traffic flow, once you're at, for example, at this point up here, then the capacity of the moving bottleneck is lower than the inflow. So that will cause some congestion to appear. And you can find what congestion that is by essentially pulling a line whose slope is the speed of the moving bottleneck, and then seeing where it intersects the flux function of the rest of the road. So in this case, you will get something that looks like this. We have some congestion upstream of a moving bottleneck and some lower density traffic downstream. This is congestion here. This is the free flow that is downstream. The thing is, you can find many solutions. What we pick is this. Again, not going to get too deep into the mathematical problems. What we're interested in here is the solutions that maximize the overtake, the flow moving past the moving bottleneck, so the overtaking flow essentially. Why that? Well, that is because the traffic density in the zone of the moving bottleneck, it will be basically here, and then you have this flow, or the densities upstream and downstream defined by this line. Again, kinematics, it's nothing too fancy. It's just something that you need to think about a bit. All right, so that's it, more or less it, when it comes to actuation. What about measurements? So even if you do not consider that you have measurements of the nearby, even if you do not consider that you have a fully connected and autonomous vehicle, I mentioned that you can do a lot with just the trajectory of some individual vehicles, for example, provided by the phone. So that is one part, the own trajectory of the CAV. The other part is all of these CAVs, especially, well, if they are autonomous, they do need to have a sensor suite that gets some sort of a situation awareness around them, because, yeah, I mean, otherwise they crash. And you can think about using this kind of information to get not only the information about the ego vehicle, but also about the vehicle that are around. Right, so what we're hoping to do is to detect and track the nearby vehicles using whatever we have at our disposal. What we hope to get from that is the trajectories of all of the vehicles. And if you look at this plot here, what I'm showing is a bunch of trajectories of a simulated road. And this plot up here is down this dashed line issue. I'm not sure how visible it is, but if you go down this dashed line, each vertical line represents the presence of a single vehicle. So what you can see is there is some higher density of vehicles around here, and that corresponds to this zone here. It might not be very visible, but there are this area here is indeed bluer. Now, if you have all of these trajectories, well, what do you do? Well, I mean, it's a bit hard to deal with thousands of trajectories of vehicles, so we will want to get some sort of a macroscopic state out of this. The kind of naive, quote-unquote, approach is to just split the road into cells. So let's do what we know how to do. Let's split the road into cells, and then just count how many vehicles you have in each of these cells, and then it's very easy to calculate the density. The problem is you get something that is very, very jagged, especially, well, you have two problems. One is if you have a very long cell, then you're averaging things way too much. The other way, if you have a very short cell, well, then you get the situation that looks like this, where you have a bunch of vehicles, and then, it basically gets very, very jittery, because small variations in how many vehicles there are will affect the density, or what you think of as density, a lot. But this is definitely the most kind of straightforward way of thinking about this. And the reason why we want very small cells is because we really want a high resolution as our vehicle is traveling on the road and so on. One perhaps better way to deal with this is to think of a bit of a smoother way of approximating this. So instead of each vehicle being represented by this kind of a point, let's smooth out the influence that each vehicle has on the traffic around it. Now, the idea is, instead of this point, let's represent the presence of a vehicle with a Gaussian. So when you do that, you get essentially a Gaussian kernel smoothed estimation of traffic density. All right, so sounds maybe a bit complicated. The way to get to it is not that tricky. But the way you can think about it is okay. First, let's have a look at what happens with if we have the trajectories of vehicles in a local area around our connected vehicle. So let's say this green vehicle, this is our connected vehicle, and it has some kind of local situation awareness. It can detect and track vehicles. Oh, this is not that visible. Vehicles in this zone. So between these two dashed green lines. So what you can do, and let's say you're interested in the local traffic density in this zone. Well, you can just count the vehicles, and sure, now the zone will be moving. You can do very similar things as before. You can just simply count the vehicles and then divide it by the length of the zone. That's your traffic density. The other way is to essentially, like I said before, instead of thinking of their presence as instead of thinking of them as being present at a point, think of their presence as a sort of a Gaussian. So you have like a smoothed out situation. And then, long story short, you replace these Diracs with Gaussian kernels, and you can do an estimation of traffic density. You can do an estimation of traffic speed, of traffic flow. You can even do an estimation of the overtaking flow. Not going to get into details. The point is, this is not that hard. As long as you know what the range that these sensors have, well, when we're talking about Gaussian kernels, you will have one scaling parameter, which is basically it's kind of like the standard deviation of this Gaussian. So if this standard deviation is too high, that will basically mean that these vehicles have a very, very non-local effect. If it is too low, then you're recovering the situation where they're at only one point on the road. So it is a bit tricky to choose this, but if you choose like 50 meters, 100 meters, you get reasonable results. But anyways, what you get from here is essentially you can assume that this connected vehicle can in some way sense the traffic density at its own position and sense the traffic speed at its own position. Why do we need that? Well, we want to reconstruct what is happening elsewhere by using these kind of local measurements. So now we're actually going to open the first block of this control loop. First, I'm going to talk about traffic state reconstruction, and then as an appendant to that, traffic state prediction. So reconstruction has to do with, okay, let's take these local measurements and try to reconstruct a more global picture. And then once we have the reconstruction of a global picture of the current state, then we want to use some sort of a simple prediction model to get the prediction of what is going to happen in the future, given how we control whatever control measures we have available. All right. And broadly speaking, well, one very simple scheme that you can employ is you can say, okay, if the true traffic state is unavailable, you use the reconstruction. Where you have, so in these plots, the green lines here represent the trajectories of your connected vehicles, and these are basically the places where you know the local traffic state. Up here you have the true traffic state, here you have the reconstructed traffic state. Simplest way you can go about it, you can say, okay, where we have local measurements, we just say the true traffic density or our estimated traffic density is equal to whatever we're measuring. Elsewhere, well, you just have to base your reconstruction on what your previous kind of guess about this position is. So basically, everywhere you just run the prediction model, except along these trajectories, you're forcing the traffic state to be equal to that what you're measuring. Turns out this kind of works. What happens is, while you're in free flow, you're not really gathering any new information because you're just moving at free flow. All of the vehicles around you are, well, still around you. But then once you start entering congestion, for mathematical reasons, you start gathering more information about the traffic flow. So basically, as this vehicle starts entering congestion, it will start detecting it. And you can see that in the reconstruction, this congestion will start appearing. And it actually also, it does not appear only locally, but its influence spreads to the rest of the road. So if you do this very simple scheme, you can reconstruct the traffic state fairly easily. At least in these kind of simple situations. All right. For the prediction side, I think due to the time constraints, I'll just run through this. One way of dealing with the PDE is you can use, well, one way is you apply numerical methods such as Godunov scheme, which comes down to discretizing the space. That is what we have with CTM. Another way is you look at front tracking, where you basically look at what happens with the discontinuities as they propagate along the road. Turns out there's a way to formulate all of that as a transition system. Not going to go into details. The point is, with this transition system, you can, it is pretty efficient at predicting what happens in the future, because you don't really get you don't need to simulate what happens with each cell. Instead, you're looking at what happens with each of these wavefronts. And the only thing you're interested in is where they collide and what happens. Then they change speed. Again, a bit too much detail to get into. The point is, you can get a fairly nice prediction fairly easily, or fairly efficient in numerical. All right, let's open another box. Let's talk about model learning. I did talk only a bit about model learning when I was presenting this kind of learning-based scheme. Well, this is kind of emulating what that learning-based scheme was looking like, because we don't really have learning that directly computes the control action. Instead, that we use the learning to get the model, and then based on that model and the prediction, then we calculate the control law. Okay, when talking about learning a model, there's basically two approaches. One is you go with a batch approach, and they usually would have some parameters, and then fit assume that you have some form of a function, and then just fit it as best you can to data. But in our case, we might be more interested in a non-parametric stream, well, both non-parametric and stream way of learning a model, because what we want to do is, as we encounter new data points, we want to kind of adjust our knowledge about the system accordingly. What do I mean by that? Well, here's how we can think about that. So let's say you can measure the local traffic density, the local traffic speed, or equivalently the local traffic flow of at the point of our sensor vehicle, and also the overtaking traffic flow in case this vehicle is moving slower than the traffic, acting as a moving bottleneck. So let's say you can measure that, you get measurements that look something like this. So you can kind of see some an outline of what this flux function might look like. And indeed, if you want to fit a piecewise linear function, then you just see, okay, where do we place this kind of a node? How do we identify all of these parameters? And then you get the flux function. You might get the flux function that looks something like this. However, you need to know how many of these pieces do you have, how many of these nodes. You need to then estimate all of the slopes. It is a bit, it can be a bit tricky. You can just say, okay, I want to estimate a triangular flux function that fits best this data. It's very easy to do. But who's to say that it is indeed a triangular flux function? Okay. What we'll be doing instead is, as new measurements come, as the vehicle senses different traffic conditions, you will be able to plot these measurements and add them as nodes, essentially, to this flux function. So what we're doing is, let's say the measurement that says the flow is this much, the density is this much, comes in. Well, we can just add a new node to our piecewise linear flux function that looks like this. So it's basically perfectly reflecting what the measurement was. Then once a new measurement from some other area comes, then okay, well, we are too far away from this node. Let's add another node. So our flux function becomes something like this. Then a new measurement comes that is close enough to this node. Then we're saying, like, okay, let's just move the node a bit and shift it so that it fits better, and so on. might sound a bit complicated. This is actually a very, very simple way to, a very, very simple algorithm. So you just keep adding these new nodes. You will see what that will essentially do in simulations and a bit later. Now, another thing that you can do is you can take, if you have this kind of local information, you can think even about, okay, let's design some sort of an experiment that we hope will help us kind of sample the flux function. So let's say you have a vehicle that is now it's going slow. It was moving fast, so now it starts moving slowly, and you can see that the vehicles behind it are starting to accumulate. So it is acting as a moving bottleneck, of course. Yeah, so we start going fast, then we slow down, vehicles start accumulating, and then you have some sort of a traffic density upstream and some sort of a traffic density downstream. So what we can do is we can detect and track these nearby vehicles, then extract from their trajectories the steady states upstream and downstream, as well as the measured overtaking flow. You can get the overtaking flow very easily. You just count how many vehicles are overtaking you, take into account your speed and their speed, and that's it. So what you get is, by doing this, you're essentially sampling some points on the flux function, and you can repeat this for different speeds of our test vehicle or of our control vehicle, and then get use the collected data to learn the model of both the model of the traffic overall, but also how this connected vehicle is affecting the traffic. So what does that look like? So let's say the traffic, the overall is modeled by this green shields flux function. And this moving bottleneck diagram that I was talking about is according to this red function. So basically, next to the moving bottleneck, we have, of course, a lower capacity because it is taking up one lane. So these points upstream and downstream will, in essence, correspond to the point here. So the blue point here will be the point downstream. The red point here corresponds to the traffic density immediately upstream, and the slope of this line is simply the speed of our moving bottleneck. And you can also see the overtaking flow, which will be where this line intersects the y-axis. If you have this point and this point, you can just draw a line through them, right? So density upstream, density downstream, and overtaking flow defines this line for you. All right, let's say we start with a fast-moving vehicle, then we have another experiment where it's moving a bit slower, now a bit slower, then a bit slower, and so on. So you can see that you're kind of sampling this big flux function, and you will get, based on these points that you collect, you can just get a convex shell or a convex hull of these points, and this gives you a piecewise linear flux function. That describes the road overall. Now, when it comes to the flux function of the bottleneck zone, there what you can use is you can have all of these lines that you were plotting, and then just have a lower concave envelope of the lines. You get a piecewise linear flux function, or a much simpler thing that you can do is you can kind of estimate. Okay, let's minimize let's see the point that is the least, where you're minimizing the distance to all of these points. And by doing that, you can get basically a parametric estimation of what this flux function will look like. Okay, that's a lot of math and talk. What does it look like in kind of, not reality, but at least in experiment? So we ran these things in Sumo. This gray cloud is basically all of the measurements that we collected, and you can again see the red points and the blue points, which correspond to the zone downstream of our test vehicle and upstream of the test vehicle. And based on these points, what you can get is the thick blue line corresponding to the flux function of the overall road, and then you can get two estimates of the moving bottleneck flux function. Now, plugging that into simulations, you can see that you actually end up with a traffic situation or traffic simulation of traffic density that fits quite well actually with what you get from Sumo. So this is based on, this is a Gaussian kernel approximation of the traffic density based on all of the trajectories of the vehicles. This is using the front tracking model and plugging in these flux functions that we just estimated. And you can see that there's quite a bit of overlap, or there's quite a bit of a match. You can see that, okay, by the way, the red line is the trajectory of our test vehicle. What's happening is it was going fast, then it slowed down, it's going slow. It was acting as a moving bottleneck. There's some congestion building up upstream, and then it continues going fast. You can see that just visually looking, yeah, I mean, it kind of corresponds to what's going on. And this is in the case of heavy traffic. In case of light traffic, you get the similar kind of a match. So here, there's not that much vehicles accumulating at this moving bottleneck, and the prediction model correctly does predict that. All right. Finally, we come to the meat of the problem and to the actual Lagrangian control part of the talk. So again, what are we trying to do? Well, we do want to minimize the total time spent. And this is, by the way, now we're kind of talking about a prediction-based control or an optimization-based control, similar to MPC or stuff. And this is the way you would basically define how you find the control. So it is just a minimization problem. You want to minimize total time spent, or rather, you want to find the controls that minimize the total time spent, but then you need to respect the dynamics of the model. So what's happening in your prediction needs to correspond to what's happening in the model. And you also need to respect some constraints on the controlled vehicles and maybe also some other constraints due to traffic. In this case, these constraints are going to be simply, we're going to simply say our controlled vehicle cannot go slower than, well, cannot have a reference speed lower than some point and cannot have a reference speed higher than the traffic, than the speed limit, essentially. The reason why we're doing that is because otherwise you might get situations where you're just telling vehicles, okay, just stop, come to a full stop at the highway, and that might not be might not be smart. So you do have to limit the minimum speeds up, like, I don't know, 80 kilometers per hour or something reasonable for safety. And as I hinted, we will be using these vehicles as Lagrangian actuators and controlling their speed. That is one control input that we will have, and then we will also try to control the overtaking flow. I will come to that in a bit. First, how do we think about congestion reduction in this kind of a framework? What is this cost function that we want to minimize? Well, it turns out that it is enough, so you can't just integrate, okay, let's see how much time each vehicle spends on the road, and then that gives you the actual total time spent. Turns out it is equivalent to minimize the early outflow from the system. If you're minimizing that, effectively what you're doing is minimizing the total time spent. So what that allows you is to kind of reason about what the control needs to be doing. So for one, if there is no obstructions, if there are no obstructions on the road, then somewhat logically you would want the traffic flow to be close to the capacity. However, if you do have some sort of an obstruction, like in this case a bottleneck, then your control logic switches to first dealing with this capacity drop due to the bottlenecks, as we had in the case of ramp metering. And once you're done with that, so this can be due to a stationary bottleneck or a stop and go wave. Now, once you have reduced the inflow to this congestion enough, so that it dissipates and eliminates this capacity drop, then after that you want to keep the inflow or the flow of traffic along the road as close as possible to the capacity, as we had in the situation in the beginning. So the only difference, if you think about this, the only difference between this kind of an approach and a ramp meter is that with ramp metering, you're basically shifting the congestion from the road to the on-ramps. Here, we're kind of like what we had in the variable speed limits case. We're shifting the congestion from the place where we have capacity drop to the place where we are controlling the traffic flow. But by ensuring that this congestion is less severe than this congestion here, we are recovering a higher portion of the traffic of the capacity of the road. Now, in order to be able to do this, what we need to be able to restrict the inflow to this congestion to a value that is lower than the outflow from the congestion. Because if the outflow is higher than the inflow, then the congestion will be shrinking and eventually it will disappear. Now, that is easy to do if we can block like 2 lanes out of 3. We're probably going to be able to do that. And also, if we have 2 lanes and only a single vehicle, probably we're going to be able to do that. But once we have more and more lanes and only a single vehicle, we might start running into some problems. So depending on what kind of congestion we have down here, our single vehicle might not be able to safely obstruct the traffic enough. Again, think back to the police car. Start swerving around, yeah, you're going to block the traffic, but I would not call that a safe maneuver. Instead, what we want to do in this case, or what we are trying to do in this case, is you can apply some sort of a multi-step control scheme. And you can think of it like this. So first, so if you cannot do it with one vehicle, let's do it with multiple vehicles. So if we do not have a platoon of these vehicles or a group of these vehicles formed already, then what you need to do is first, okay, let's collect at some point. And at that point, we are a unit. And now that we have 2-3 vehicles, now we can control the traffic more, and we have more ability to control the traffic. So the way we can do that is first we select an initial point where we start accumulating these connected vehicles or autonomous vehicles. Now, we do need to make sure that this point, so in this case it is here, and this point needs to be in a place where you have enough connected vehicles around, because otherwise you're never going to be able to connect enough. But it also needs to be just the right distance from the congestion that you're trying to eliminate. Because if you start collecting them too close, it will take too much time to collect them. You will not be able to you will not be able to apply enough control to dissipate the congestion. What will end up happening is you will get some congestion. You will remove a part of the congestion, but then you will run into this, in this case, phantom jam, and then the vehicles that you've been holding up just get added back into the congestion if you haven't done anything. Instead, you need to start a good distance from the phantom jam. Then you basically tell the vehicles downstream of this, or the collected vehicles downstream of this point, to slow down. You tell the vehicles upstream to keep going fast, and then as these vehicles join, you keep getting a higher and higher number of them. Then once you have enough, then you start having them act as a moving bottleneck. And by having them act as a moving bottleneck, they're restricting the traffic flow that is overtaking them. And then this traffic flow that reaches this phantom jam is lower than the outflow. Therefore, this congestion will dissipate after some point, and we recover free flow. Okay. Now, depending on what kind of a penetration rate you have, well, for one, if there are no connected vehicles, obviously you cannot do anything. If there's no vehicles we can control, we don't have control over the system. 0% penetration rate, this phantom jam just keeps existing forever, quote unquote. Even with a very low penetration rate, you might be able to get enough vehicles that you start. It might take a while for these vehicles to kind of form into a unit, but after that, you have enough control. You can restrict the inflow to the phantom jam and dissipate it. The higher penetration rate you have, the faster you will be able to gather enough vehicles. So basically, if you think about it like this, if you have a 3-lane road, if you block 2 lanes, which you can kind of do with 2 vehicles, you're probably going to do fine. So depending on what the density of connected vehicles you have, it will take a different amount of time for 2 of these vehicles to join and create a unit that you can then use to control the traffic. All right, so that basically covers everything. I have now completed the Lagrangian traffic control loop. So to recap a bit, we collect the local measurements around these connected autonomous vehicles. as the only measurement of the traffic state. We use these measurements and plug them into some model learning mechanism to learn the model that we then use to reconstruct the traffic state as well as predict the future evolution of the traffic state. Then we use this prediction to calculate the control actions for all of these connected autonomous vehicles. And then finally, all of these CAVs are actually the actuators that are applying these control actions and affecting the traffic flow. So finally, time for some simulations. So we have a scenario where we have randomly arriving phantom jams. So we have some sort of a road. From the downstream end of this road, we, in this case, generate artificially phantom jams. So you can think about this being some sort of on-ramp, and then based on how many vehicles are arriving, there might be some phantom jams forming there. Okay. You have randomly arriving stop-and-go waves appearing at the downstream end, so at the end of the road. And we want to dissipate them by using multiple connected vehicles acting as a controlled moving bottlenecks, and both controlled moving bottlenecks, so actuators and sensors. So we're only relying on the data that we get from them. We're only relying on the control that they can implement. So here we have connected autonomous vehicles arriving at a random rate on the upstream end of the road. And we are comparing 3 levels of information available. So first, in the case we have no control, you can see that these, by the way, the trajectories of connected vehicles are shown in red. Again, it's not maybe not that easy to see, but they are basically traveling along. Then some of them, if we're not controlling them, then they will pass through this congestion and then continue on. So nothing too crazy happening. At least in the no control case, nothing too crazy happening. What you have here is some of these phantom jams will persist. So this one, actually, there was not enough inflow to keep it living. This one had enough inflow, and you will see it simply sweeps across the whole road and then exits the system. Now, this is what we have in case we are applying no control. The other extreme is, let's assume we actually know all of the information about the traffic on the road and just use these connected vehicles to dissipate these stop-and-go waves or these phantom jams. What you can see in this case is, yeah, I mean, we are indeed successful. So with this stop-and-go wave in particular, you can see that immediately as it enters the road, we start dissipating it. These 2 vehicles are not able to dissipate it because they have limits on how slow they can go. But this one indeed is able, and the stop-and-go wave dissipates at this point, and it's no longer causing an obstruction for the traffic flow. Similar thing happens here, similar thing happens here. So basically, we are able to keep the traffic state the traffic in a much more fluid state. The interesting case is when we have a reconstruction-based control. So in this case, you can see that once this stop-and-go wave enters the road, we do not immediately react to that, because in this case, this vehicle does not quite identify it. But once this vehicle here goes through this stop-and-go wave, it is only then that we start reacting. So we are able still to dissipate this stop-and-go wave, but it does take a bit more time because we are slower to act, because we are slower to notice it. So what is happening here is we have in parallel model learning, traffic state reconstruction, and actuation, all done by all done relying only on these connected vehicles. So overall, you can see that the situation is so in case we have no control, we have quite a bit of delay compared to if there were no phantom jams occurring on the road. In contrast, in case we have full information control, we can almost eliminate the entire delay from the system. And the case where we're using a reconstruction-based control lies somewhere in between, but we're still able to do quite a bit, even though we don't have the assumption that we know exactly what's happening in the system. Okay. Now, this is how in this case, this is how the process of learning the flux function looks like. So first, a measurement appears here that deviates enough from what we until that point assumed was the flux function. We change the flux function like this. then we get the new measurement. So in this case, it is close enough to this point that we will shift this breakpoint of the flux function. Then as new measurements start arriving, we will further shift this point. And then finally, once we get some measurement around here, then we will actually start breaking re-breaking this flux function. And you can see that it starts kind of assuming the shape of this dashed line, which this dashed line is the kind of ground truth flux function in this case. I will give a bit of a taste only, so I will only show the simulation result and talk a bit about another control scheme. So in this case, we were thinking about, okay, how can we use platoons, already formed platoons that are arriving on the road? How can we use it in this case for bottleneck decongestion? So far we were talking about dissipating phantom jams. Let's see what the situation is with a stationary bottleneck. So in this case, what we are doing is we have a very similar situation. Well, in this case, one thing is different. We do assume that we know the full state of the road. So we're not focusing on the sensing part. What we get from these platoons that are arriving are, in this case, just their own states. So their own position, well, basically only their own position. Then, like I said, we assume that we know the full traffic state on the road of road in question. Then what we want to do is feed this into some sort of a prediction model. It's a queuing model with moving queues, not going to go into details. Based on that, we calculate two control actions for each of the platoons. One is what the speed should be, that it is what its heading speed should be. The other one is what its formation should be. And what I mean by formation is, should it only take one lane or should it take two lanes like this? So in this case, we have a 3-lane road. We have 1-lane drop. So hopefully, if we block 2 lanes, even though we have capacity drop here, we will be able to restrict the traffic flow more than the outflow from this bottleneck is, and dissipate the traffic density, dissipate the congestion. Now, another thing that we're doing here is we are playing with where exactly do we implement this control. So if we have a bottleneck at Lyon, do we start acting in Grenoble or do we start acting closer? So probably we should start acting closer. All right, so this is what the simulations look like in this case. So here the bottleneck we have at the 20th kilometer, and it is represented by this dashed red line. So in case we have no control, you can see that there is quite some congestion that builds up at this bottleneck. Almost immediately there is a traffic breakdown, and then a lot of congestion builds up. So this is the case where we have no control. And zooming in, what you can see is these dotted lines, which I'm sure are pretty hard to see. Those are actually the trajectories of our platoons that we are assuming are just arriving at the system with according to a Poisson process. All right, so first attempt, we can say, okay, let's take this whole road segment of 20 kilometers and let's immediately start acting as soon as we predict that there will be a capacity drop at the bottleneck. So you can see that the situation in this case is quite a bit better. There is almost all of the congestion at the bottleneck is gone. Because of that, there is less capacity drop. We are much more efficient. The overall traffic state is much better, and that also reflects on the total delay that all of the vehicles are experiencing. So this was the uncontrolled case. This is the case when we're controlling the whole road. Now, if we zoom in, it's actually interesting to see what happens here. You can see that this is an interesting case. So at this point, we already predicted that there will be some traffic breakdown happening. What that tells us is, okay, we need to delay the inflow of some traffic. And in this case, we're pretty good actually when it comes to the prediction because we know the model, all right? And what ends up happening is we react way, way, way before we actually need to react. So we have these vehicles hold up some traffic 20 kilometers away from this bottleneck. So is that, I mean, is that smart? Well, maybe. I mean, the results are quite nice. We eliminated the capacity drop. In reality, it will be very, very difficult to predict what happens over this long a time horizon. So basically what we need to do is predict what will happen when the traffic from this position reaches the bottleneck. So we have a perfect way to predict that. Yeah, sure. Let's say we can do that. Otherwise, it's probably better to wait until we're closer. And that's indeed what we do with the third scheme. So I mentioned that we will be shifting what is exactly the area in which we are trying to do control. And this area, in this case, is represented by these dashed red lines. So the downstream end of this area is obviously the bottleneck. The upstream end will, in this case, now shift. So what we're doing now is, I'll zoom in again. What we're doing now is, you can see that the boundary here, we will actually dynamically change it based on the traffic state inside of this area. So we're only focusing in this case on, well, in this case, it starts with 1 kilometer. Then we're basically saying, okay, if we can dissipate all of the congestion at this, well, all the future congestion at this bottleneck by only acting within this 1 kilometer, that's great. We don't need to extend our control zone. If we predict we are not going to be able to do that, then we do indeed extend that. The result is that you still have quite a similar situation at the bottleneck. So the bottleneck is also most of the time in free flow, but the congestion is much more kind of localized. So we keep the congestion close to the bottleneck, but not at the bottleneck, right? So, and by doing that, there's another benefit of this, and that is that it is much easier to predict what effect the vehicles will have on the bottleneck. Because if you're predicting what the effect of what you do 20 kilometers away from a bottleneck will be on the bottleneck, then you need to predict all the way up to the time when the vehicles from this point reach the bottleneck. So basically, if you're doing a shorter term prediction in the sense of space, then you will need to do a prediction that is shorter in the sense of time. So the reason why we were doing this is to speed up the calculations, as well as to what I said, keep this congestion closer to the bottleneck. And turns out what we get as the results, as the total time spent, is quite close to the case when we were controlling everything over the whole length of the road. But trust me, the calculations for this were much faster. And that brings us to the end. So the only thing that's left to do is to conclude. I started the talk by asking how can we reduce the traffic congestion using both classical and emergent traffic control. I hope I've given you at least some answers. Yeah, I mean, just to kind of analyze the situation, you have the road system, which is one of the largest and one of the most economically, at least, and important systems, but there is actually very little control happening on it. Now, should we do more control? I don't know. Maybe you would not like to be stopped by a ramp meter every time you're entering the highway, but you could argue that if we can improve the efficiency of the whole system, then it would probably be worth it. And I've shown some traffic control measures, and I hope I've shown, at least from a theoretical perspective, how we could still improve the traffic situation by implementing the control measures that require much smaller investments. So we do not need to all of the sensors and actuators everywhere along the road. If we have some communication equipment, and if we can communicate with the vehicles, we can still do quite a bit. So to take matters to an even more extreme level, we definitely don't need to improve the infrastructure. So we can always build more roads. The question is, should we? Well, the answer is probably not. And the main point of this whole thing was that the connected vehicles bring indeed an enormous potential for traffic control on both the sensing and the actuation side. And we do, however, well, both the connected vehicles and the Lagrangian traffic control, I do think they add a lot of potential on both the sensing and the actuation side. And of course, using this Lagrangian data that we already now have available in some sense through the phones, we should be able to estimate the traffic state to quite a high degree, to quite a high level of detail. However, the caveat is that we have most experience with classical traffic control measures. So there does need to be a bit of a paradigm shift in how we think about how we model the traffic. So there definitely does need to be a bit of a push towards traffic models that are a bit more kind of adjusted to the Lagrangian actuation and sensing. And instead of some kind of future work, there are some, here's just a short list of things that I thought were interesting potential future research directions. For example, well, for one, this kind of Lagrangian traffic data, in particular these vehicle trajectories, sure, you can use them to estimate the traffic density, but you can use them for so much more. So in these kind of simulations, what we tried to estimate was the effect of a vehicle acting as a moving bottleneck. That is one example of what they call here a important traffic phenomenon. But you can use them also to get an insight into much more things. You can use them, for example, to see how, and I mean, that there is research on these kind of things, to see how the weaving and lane changing affects the traffic flow. You can use them. Yeah, there's really a lot of traffic phenomena that you might be interested in. And these kind of data can help you a lot with understanding them. Now, when it comes to what we did here, or what I did during my PhD, all of this was, well, almost all of it was on a purely macroscopic level. A lot of these things, you really need to plug them into microscopic simulations and then check if what you predicted would happen in your macroscopic level still holds in a microscopic level. So with that in mind, all of this control that I was doing with a single vehicle acting as a moving bottleneck, blah, 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 that all needs to be plugged into exhaustive microscopic simulations and then see what happens. Hopefully the same thing happens. We don't know before we see. And then the next step after that is, of course, putting this show on the road and trying to do some real world experiments. So actually putting these vehicles and controlling the vehicles on the roads themselves. So kind of related to that, all of these kind of maneuvers involving multiple vehicles. So with one vehicle, kind of know what you are up to. Moving bottleneck seems to be the way to do that. Seems to be the way to explain how a vehicle is affecting the traffic. But if you have multiple vehicles, then I think the questions there's still a lot of open questions in how exactly do these complex maneuvers with vehicles reordering themselves, moving around, how does this all affect the overall traffic? And finally, I have a thing that I think would be really interesting, which is here in all of this talk, I assume that we have perfect control over some vehicles. So we can exactly tell them, okay, you go at 80 kilometers per hour and they go at 80 kilometers per hour, unless they enter congestion. In that case, they will be going slower. One interesting thing, which also kind of harkens back to variable speed limits. Because, okay, you have a variable speed limits that says go 80 kilometers per hour. How many people do actually follow these? Well, especially if it's advisory, not 100%. So you do not have full compliance. Well, if you think about Lagrangian traffic control with not full compliance, then you also end up with some interesting problems where you can tell the vehicle, or ask the vehicle, go slower, please, maybe give it some incentives, but you have no guarantees that it will actually follow your control. So, I mean, you could even think of an app offering, like Waze, offering drivers some money for acting as a moving bottleneck or something of the sort. I don't know. I think it would be interesting to try that. I have no idea what the results would be. So with that, thank you for your attention. And any questions that we have left over, I would be very happy to take them.